Okay, so in the previous video, we showed that there's some discrepancy between the narrowband and wideband approximations. We saw that the narrowband approximation was going to give us a bandwidth of 2 times b. But in the wideband approximation using the staircase method, even in the best case scenario, we saw that that approximation was going to give us 4 times b. So it's going to be twice as large using that staircase method. So clearly the staircase method got us on the right track for approximating a wideband signal, but it's probably still too large to actually be accurate. So let's see if we can come up with a reason that for this difference. So the staircase method must have over-approximated the bandwidth, and this kind of makes sense because when we're looking at the staircase, we're breaking that staircase in time into those rectangular boxes. And when we take those rectangular boxes and convert them into frequency, that's going to give us those sync pulses that really spread out in the frequency domain. So that's probably going to cause us to over-approximate the bandwidth. So instead, let's come up with this compromise solution, and let's call it Carson's rule. And in this Carson's rule, we basically took our wideband approximation and made it smaller. We divided it by 2. And let's keep this delta f as being equal to the constant times np over 2 pi. And so we can then see, using the Carson's rule, that if indeed delta f is very small and we have a truly narrowband signal, our Carson's rule approximation will reduce down to 2b bandwidth. And that makes sense because we analyzed the narrowband part analytically and found that it should be very close to 2b bandwidth for a narrowband signal. But if delta f is very large and we have a truly wideband signal, then that means that the term with delta f is going to really dominate the bandwidth approximation. And that's going to give us a bandwidth approximation of 2 times that delta f hertz. So if we use Carson's rule approximation, we can see that we have 2 different approximations, one for a truly wideband signal and one for a truly narrowband signal. And now we can see what the original error in our thinking was. So if you think back to when we first started talking about angle modulation, we said that, well, maybe if we try frequency modulation and we make the constant kf very small, we thought that maybe, just maybe, we could transmit a signal that used 0 bandwidth. And so the incorrect assumption that the original frequency modulating, original investigators of frequency modulation thought was that this frequency bandwidth on the left for wideband signals, they thought that that would apply to narrowband signals. However, it does not. So no matter what, if you're transmitting using a frequency modulated signal, you're still going to have some bandwidth. And even if you set kf to 0, there's still going to be some other terms that are going to add into the expression for the bandwidth of the frequency modulated signal, and it's going to be at least 2 times the bandwidth of the message. All right, so let's do one more thing, and let's define a ratio between delta f and the bandwidth of the message, and let's call that beta. And beta is going to be the modulation index, which will allow us to rewrite the expression for the bandwidth of the frequency modulated signal as 2 times b multiplied by beta plus 1. And when we write it this way, this index, beta, is similar to the amplitude modulated index, mu. And what about phase modulation? How can we approximate its bandwidth? Well, you can use the same method. You just have to remember that the derivative of the message is equal to this m dot t. We can break up the derivative of the message so that each point of the derivative of the message can be divided into cells. And each cell is going to have a different height, m dot tk, and each height, m dot tk, is going to give us a different instantaneous frequency and time. So each one of these cells is going to have a constant instantaneous frequency that's related to the derivative of the message instead of the message itself. So if we did that for everything in the phase modulated signal, we're going to have some highest value of the derivative of the modulated signal and some lowest value of the derivative of the message. And that difference from high to low is going to be delta f, k times the maximum of the derivative minus the minimum of the derivative divided by 2. And if we change this expression for delta f for phase modulation, we're going to have a slightly different expression for beta. And for the typical zero offset case, we can have a even more simple expression for delta f. And that's going to give us a bandwidth approximation for phase modulation that looks like this, or using beta, it looks like this. All right, so now let's compare the two. So the bandwidth of the frequency modulated signal depends on the peak value of the message. However, the bandwidth of the phase modulated signal depends on the peak value of the derivative of the message. If a message has a lot of high frequency components, that means that it's going to have a lot of rapid time variation. Signals that have a lot of rapid time variation are going to have large values in their derivatives. So that means that the bandwidth of a phase modulated signal is going to depend a lot on the frequency components of the original message. However, the bandwidth of a frequency modulated signal doesn't really depend on the frequency components of the message at all. So if the frequency components of the message are mainly at low frequencies, then the bandwidth of a phase modulated signal is going to be small. And for frequency modulation, if the message in time has small amplitude, or the value of kf is small, then it will have small bandwidth.